If you want to learn how to implement the counterfactual regret minimization algorithm in Python for the game of Kuhn poker, then you're in the right place. I've done it. I'll give you the code. I'll take you through the code. I'll tell you about a few of the pitfalls that I found along the way. I'll give you some notation to make the calculations easier for you to perform on your own. One prerequisite to this video, the CFR algorithm was explained very well by a guy named Professor Bryce. He's on YouTube. I'll link him in the description below. And he's actually got an entire playlist. So if you're just coming from scratch, you don't know anything, you can go through his entire playlist. He'll take you through the basics of game theory, and it culminates in him talking about the counterfactual regret minimization algorithm. He does a great job of explaining everything along the way, but he doesn't quite get there to help you to implement the algorithm in code. So this video is really a piggyback off of his series of great videos to help you actually turn what he's telling you in the videos and what you learn through his video series into actual code that iterates through and does converge upon the Nash equilibrium. So if you're ready, let's get started. So this is how Professor Bryce represents info sets in his videos. So this would be representing the info set where player 1 knows he has a king, but he's not sure whether player 2 has a queen or a jack. So this little dotted line connects these two specific nodes, and together those nodes form an info set. And the way it works is each level is a different player's info set. So this first level will be player 1's info sets, the second level will be player 2's info sets, and then it goes back to player 1's info sets on the third row, etc. And every one of these nodes in the second row would be paired to another node that I haven't drawn here. And essentially, this is a more complicated way to represent this information. I'm going to introduce a more concise way to represent an info set that really helped me while I was implementing the algorithm. So this is my simpler way of representing an info set. So I've replaced the circles with boxes because the circles were specifying specific hold cards that both players could hold. Instead, the boxes now are specifying entire info sets. So this box with a king at the top simply means that player 1 has a king, but he's unsure if the other player has a jack or a queen. So this is actually equivalent to all of that in the previous drawing. And again, we have, just like we did for the last drawing, the info sets on the first row belong to player 1. On the second row, they belong to player 2. On the third row, they belong to player 1 again. And you can tell that by simply just the length of the info set, because if it's got no actions here, then that means no one has acted yet, so it's still player 1's turn, so that's player 1's info set. If it's got a single action there, then that means that player 1's acted and it's player 2's turn to act, so that must be player 2's info set, etc. And if it's got another one, so, say we came down here and player 2 decided to bet. So that would look like this in this type of drawing. So both players know the actions that have taken place. They're pass bet. So really the only difference between the information sets for player 1 and player 2 are the cards. And so when you draw it like this, rather than it kind of constantly spreading out like it does in Professor Bryce's drawings, where every node gives birth to two more nodes and it just keeps growing as you go down, you actually get this phenomena of it kind of coming back together. And so the next row would have two info sets, and then it would come back together into one info set in the row after that, etc. And so this is actually going to make just kind of the notation way simpler. The way we think about it will be way simpler, and it really helped me in implementing this algorithm. I want to point out one more thing before we get started here. Professor Bryce draws out the entire game tree, and he talks about traversing the tree and updating beliefs on the way down, updating the utilities on the way back up. And I believe, although he doesn't I don't think he says it in the videos. I think he's talking about a breadth first search there, because you need to use the values from previous rows or later rows in order to update each row, and they're not necessarily direct ancestors. The values, for instance, so he's got this whole tree here, and sometimes in order to update this node, I need to use a value from this node up here. Well, if I'm doing a depth first search, I'm going to update the beliefs in this one, that one, that one, and then I'll update it in this one. But in order to update the beliefs in this one, I might need to use the beliefs from that one. So depth first search is not going to work. So if you were going to implement this with a depth first search, I would not advise that. You want to use breadth first search, so that you go row by row. So you take the first row, and then the second row, and then the third row. This one's the only one that's going to work. But I just want to point out that none of this is necessary. So I'm going to back out of everything I just did. And I just want to show why that's not necessary. So if you gave me this info set, I know what its ancestors are. So that's going to be Queen P and Jack P. So, and at those info sets, whichever one we're in, whether player 2 was dealt a queen and they saw player 1 pass first. So this would be the full tree in the new notation. And notice I easily made that from being given the resultant info set. So that is why the tree is not necessary, is because we know how these nodes are connected. In a more general graph or something, you might give me a graph where, okay, node 1 is connected to 4 other nodes, and then this node's only connected to 1 other node, and this node's connected to 2. So it could be any number of connections, and the connections could be, don't necessarily follow some simple paradigm. That's why you would need maybe a tree or something like that. And trees, binary search trees are useful for finding data and whatnot. But we can specify each of the info sets by a hash key, which is this would be the hash key for that info set. So KPB, I can store this in a hash map, and then I can say, okay, I want the ancestors of this, because I need, these ancestors play a role in determining the value of KPB, but I don't want to traverse a tree to find them. I'm just going to send this key into a function, send that key into a function, and it's going to spit out, here are the ancestors. And then I can look up each of these hash keys in my hash map. So hopefully that makes sense. We don't need to use a tree traversal, and I think it's just overkill for this problem. And it's the reason that we don't need to use the tree is because we know how the nodes are connected. And if you give me a node, I can give you all of its descendants and its ancestors, and I don't need you to give me the tree in order to do that. I can discern what the descendants and ancestors are simply from the string, simply because of the easy and reproducible and predictable way that these nodes are connected to one another. The first part of the algorithm is to calculate beliefs, and Dr. Bryce talks about downwardly traversing the tree, and he's right in the sense that obviously to calculate beliefs here I need to use information from previous levels, but my implementation doesn't implement as a tree. As I've said before, I think that's overkill for this problem. First of all, the game space of Kuhn poker is very small, so there's not memory issues or anything there. But also, and most importantly, you can traverse the tree without actually having a tree, because I can predict all the connections. So if I'm trying to get the ancestors of this info set, then I can write a function that gives me the ancestors of that info set. So, and I can implement this as just, I pass in a string that describes the info set, and it outputs me 2 strings that that are the hash keys for its ancestors. And so I essentially can traverse a hash map similarly to the way I would traverse a tree. And it just makes the implementation way easier because as I discussed before, you might be down here and this node, in order to calculate something for this node, it actually needs something from this node. Well, traversing a tree to get that information, that's a little more complicated. If I'm just using a hash map though, I say, okay, I need stuff from this one, I can jump right to it. So I think the implementation personally is easier with the hash map. That being said, so let's talk about how beliefs are calculated. So anytime you're thinking about calculating beliefs, I just want you to imagine this little diagram of info sets. So this info set down here at the bottom is the one we're calculating beliefs for, say. So we just saw that our opponent, player 2, chose to bet, and we're going to use that information to try to figure out what the probability is that he has a queen or a jack. So, up here in this info set, I haven't seen him act yet, so it's 50-50 whether he's got a queen or a jack. But down here, where I've seen him bet, well, that gives me a little information, because say he bets 100% of the time when he has a queen and only 50% of the time when he has a jack, then I can use that information to discern, hey, there's like a 66.6% chance that he's got a queen right now. And Professor Bryce goes over those calculations and whatnot, but I just want you to imagine those calculations in the terms of this graph. It'll really help you in your implementation of this. Before moving on to calculating utilities, I want to talk a little bit more about calculating beliefs for a more general game than Kuhn poker. So Kuhn poker is very simple because at every info set, the player deciding what to do with that info set has at most seen their opponent make one action. So at this info set, the player 2 is deciding what to do at this info set, because this is player 1's decision, this is player 2's, this is player 1's, player 2's. This down here at the bottom, by the way, is not Kuhn poker. This is the generalization that I'll speak of. But let's just take this one for right now. So at this information set, player 2 has seen player 1 pass. So they've only seen them do one thing. At this information set, player 1 has only seen player 2 act once. And in Kuhn poker, there wouldn't be info sets past this. Player 1 would make a decision based upon the one action that he's seen from player 2, and the round would be over. And so calculating beliefs is a little simpler in this case. So I gave the example of, okay, well, if player 2 is in the information set queen P, they bet 100% of the time. But if they're in their information set jack P, they only bet 50% of the time. So these would be their strategies. And their strategies are our strategies, because this is self-play, so we're assuming that they're playing the same strategy we are, essentially. So we can use the information that they bet and our knowledge of how often they bet in each situation to calculate the probability that they have a queen. So instead of writing 100 there, I'm going to put 1 divided by 1 plus 1/2. So this is the probability, the amount of time that they bet when they have a queen, divided by the amount of time that they bet when they have a queen, plus the amount of time that they bet when they have a jack, because these are the only possibilities. So at any rate, you can think about how to calculate that on your own. That's not really the point of this video, but the beliefs in this case would be 2/3, 1/3 for queen jack. So if I see them bet, I use that information and discern that they have a queen 2/3 of the time. Now, what if the game was a little bit more complicated than this, though? Then the calculation would be more complicated. So let's say when they bet, I have a choice to raise them. So I choose to raise, and then they re-raise me. And so these last two actions are two raises. This is not Kuhn poker anymore. This is some other game where you're allowed to raise and re-raise. So what would the belief calculation be here? Well, they either have a queen or a jack, and they're going to have that the whole time. So they're either like kind of on this side of things, or they're on this jack side of things. And I'm just going to get rid of those marks that I just made. But they're either on the left side of the graph or the right side of the graph. And so you ask, okay, well, what's the probability that I would have observed a bet and a re-raise from them in these situations? And we'll say that we know their strategy at every point. So let's say that this is like 75% of the time that they're in this info set, they'll choose to bet, and this one is 50% again. So what is the calculation there? The calculation ends up being 1 times 0.75 divided by 1 times 0.75 plus 1/2 times 1/2. Okay, so this is basically saying they either have a queen, in which case the probability that we would have seen a bet and then a raise is the probability that they bet in the first case times the probability that they raise, because these are kind of independent random samples in a sense, and you can think about that later on your own. Again, I don't want to get too in the weeds with the math here, but this is how you would calculate that. And so you can see that we could, in a more complicated game, store the information. So we're kind of like adding up these factors. This is kind of a cumulative factor for the queen side of things. So this is 100%, and this set 0.75 is this 75%. And then on the jack side of things, it's, if I was calculating for jacks, it would be 0.5 times 0.5 divided by 1 times 0.75 plus 0.5 times 0.5. Sorry for the handwriting there. So this would be the calculation for jacks. This is the calculation for queens. So you can see that these two numbers are actually coming from just kind of the jack side of things. So if I wanted to, I could store along the way, kind of while I'm calculating my beliefs, I could store on each one of these info sets the cumulative, this kind of cumulative term here, and keep adding values to it as I'm traversing down the tree. And then I wouldn't have to actually like keep traversing up the tree from this point. I just use these two values and then add it to my old like kind of cumulative factor that's growing here, and I would only have to traverse back a maximum 2 levels here. So hopefully that makes sense. This is for a more complicated game that I didn't implement, but my point is that you don't have to traverse like kind of all the way up the tree there. You can kind of accumulate this information as you're going down, store it on the information sets, and then every time you're calculating a new belief in the more complicated game, you would use their strategies as we do for Kuhn, and then you would also use this extra piece of information, this cumulative factor that you've been storing that we actually don't need to use for Kuhn poker. And the reason we don't need to use it is because we never have more than one action from our opponent that we've seen. So every time we're at an info set, we have never seen more than one action. So all we have to do is this first calculation. We never have to keep this cumulative factor that keeps growing. Okay. Now I want to talk about calculating utilities. So Professor Bryce described this as a bottom-up approach. You would do it on the upward traversal of the tree. So you traverse down the tree, and then on the way back up, you would calculate utilities. And the reason you want to do it from the bottom up is pretty obvious, hopefully, that you want to start at the end of the hand where you already know who won and how much they won, and go up kind of one level at a time from there. And it's kind of intuitively obvious, hopefully, that the hardest one to calculate would be the very first one, because you would need all the information from the lower nodes. Okay, so when you're doing this, you're going to naturally kind of, if you're anything like me, you're going to start to draw it like this, because you're going to say, well, at each one of these info sets, my opponent has two uh, two different options. Don't do it like that. So that's the way Professor Bryce's graph looked, but we're doing info sets here, so we're going to draw ours a bit differently. So ours is going to look like this. So this is maybe where they both pass, this is where they both bet. So we'll put these little boxes here. This is king, bet, bet. This is king, bet, pass, where I've just taken the kind of action string that we've got so far, which is just one letter, and then just added another letter to it. So in this case, I added B. In this case, I added P. And we're again back. So importantly, and this is one of the things I want to talk about in this video. Importantly, we're talking about the info set where I'm the first player. So we're calculating the utilities for the first player now, and I know what card I have. And this would be the info sets for the second player, and this is the first player again. So we're back here at the bottom where there aren't two different cards on this bottom level. There are two different cards on this level because we're unsure what our opponent has, but we're back here where we know what we've got. So you might ask yourself, well, okay, so these are obviously terminal nodes. This is Kuhn poker, and the game is over at this point. Like, I bet he called here, and I bet he folded there. So you're gonna say, well, why can't I just take this terminal value? So the the payoffs would be 1, -2, 1, -1. If that's not clear, you probably need to watch Professor Bryce's video, but there's a $1 ante, and we both bet and called here. And then here I just win the $1 ante. Okay, so you might say, let's take these payoffs and calculate the expected utility of this level, and then we'll go up to the next level. That's not the way you do this. Actually, what you're going to do is you're going to skip 2 levels, and that's really the focus of this video, is why that is. And it's pretty simple when you think about it, actually. So the expected utility, you're not actually going to calculate the expected, and I'm going to change this back to purple. You're not actually going to calculate the expected utility of this info set. And the reason is because if you were going to calculate the expected utility of that info set, you would need to, let's say we're calculating the expected utility of betting at that info set. Because so here we're obviously calculating the expected utility of betting at the king info set. And now I'm just saying, okay, let's do it kind of for player 2. Let's say player 2 is in this info set. We're trying to calculate the expected utility for it, and we're going to say the expected utility for betting there. So that would take into account these 2 info sets. And notice that the Jack info set, yeah, sure, it goes into the expected utility of this one because this second player doesn't know that I don't have a Jack. But the Jack, there's no Jack anywhere on any of this stuff, and that's because I know that I don't have a Jack. So the problem with just moving one level is you're switching your information schema or the information landscape. You are switching what information you have. So if you skip 2 levels, you're not. You avoid that. You've got the same level, you've got the same information on every other level of these graphs. And that's essentially why you have to skip back 2 times, because you need to be in the kind of paradigm where you have the same information and you're using the same information. The calculation of this information set incorporates the possibility that you have a Jack, which we know is not true when we're calculating the expectation value of betting when we have a king. So I hope that that's clear. Just refer back to this diagram And remember that you have to skip 2 levels, and it's because of the kind of different information between the 2 players. Okay, now I want to talk about reach probabilities, or as I called them in the code, likelihoods. That may anger some people because likelihoods have a specific meaning in statistics, but I call them likelihoods. You can call them whatever you want, but let's calculate the reach probability for this info set down here. Professor Bryce briefly talks about this in his video, but I wanted to talk about it separately because it can be a little bit confusing to people how to calculate this. He didn't really go through a calculation as much. So you assume that if I'm calculating it for this info set, I'm assuming that I'm trying to get to that info set. So more general way to say that is like each info set has an owner. The owner of all the info sets on the first level is the first player. The owner of all the info sets of the second level is the second player. The owner of the info sets on the third level is the first player, and so on and so on. If we had a bigger game, it would just alternate like that all the way down. Okay, so you're assuming that the owner of the info set is trying to get to the info set. So obviously, you can tell from the fact that the last action here was pass that these are both passes, and the last action here at the bottom is bet, so this guy bet. So you completely discount or don't take into account the probability that I pass up here because I'm trying to get to those nodes. Sorry, I'm trying to get to this last node that I'm calculating the reach probability for. So I don't include these probabilities at all here. So the only probabilities that I'm concerned with are my opponent's probabilities of choosing the actions that get me to the info set that I'm talking about. And that would be all the actions along the way. So if we did have, more decisions being made here in a more complicated game, we would also need to take into account our opponent's actions here and here. But right now, since we're calculating an info set where our opponent only performed one action, then we only need to take into account their probabilities for performing that action that gets us to it. Okay, so let's do this calculation. So up here, the kind of reach probability for this one is 1/3 because 1/3 of the time I'm going to be dealt to king. The reach probability for this one down here is going to take into account my opponent's probability. So you might kind of want to calculate as 1/3 times 100% plus 1/3 times 1/2. Okay, and this will end up giving you 1/2 because it's going to be 1/3 times 3/2, which is 1/2. That's wrong. So this is incorrect. And you know it's incorrect because if you look at this reach probability for this node that you calculated down here, it should never be higher than the reach probability for this node up here because you have to reach this first node in order to reach this bottom node. So the reach probability of this first node has to be at least as high as it is for the bottom node. So, if you defined the reach probability with some function r, then you could say that the reach of KPB has to be less than or equal to the reach probability of K because K is, necessary to have in order to reach KPB. Okay, hopefully that's clear. So obviously this calculation that we did was incorrect at first. So let me erase a little bit of this and just over here on the side just show you the correct calculations. So the correct calculation would be same one that we did, 1/2, but we're also going to divide it by 1/2, and you could say that you could think of each of these as being multiplied by 1/2 because they've each got a 1/2 probability of happening over time. And that's because 1/2 of the time when I have a king, my opponent's going to have a queen. And 1/2 of the time when I have a king, my opponent's going to have a jack. So that's where this 1/2 comes from. And you might also think, well, I mean, but we have this information that they bet down here, right? So we can use our beliefs about betting to say it's not actually like 50-50 that they have a queen or a jack. It's more like 60-40 or something because they bet more often when they have a queen. Don't do that. So beliefs should not be part of your reach probability. Beliefs tell you the probability that your opponent has a specific hand based upon the information that they've given you in that hand. So it weights the probability within a single hand. But reach probabilities are about the average probability over all the hands, over a large number of hands. And obviously the probability over a large number of hands of me having a king, it's going to be 50-50 between queen and jack over many, many hands. So don't try to use this information of your beliefs and the fact that they bet to try to recalculate from 50-50 for queen and jack. Just it's always going to be 50-50 over a large number of hands, and that's what reach probabilities are. If you played 1,000,000 hands, you'd be at this info set half the time when you have a king, and you'd be at this info set half the time when you have a king. So their contributions should factor in equally, and that's why you use a 1/2 for both of them. But you put that in front, and you would end up finding this is not 1/2 as we calculated before, it's 1/4. And that is less than or equal to 1/3, so it satisfies that requirement that the reach probabilities as you go down the tree must get smaller and smaller and smaller. So yeah, that's all I wanted to say about that. That's how you calculate the likelihood. You need to divide by this extra factor that comes from the number of different hands your opponent could have, basically. So if we were playing a game with 4 cards instead of a game with 3 cards, then this would be 1/3 instead of 1/2, because when I had a king, my opponent could have a queen, jack, or a 10. Okay, I wanted to briefly expose you to this script that I wrote to find the Nash equilibrium in the Kuhn poker game. And I'm just going to show you what the script running looks like. So this is calculating the total gain per round. So the total gain is essentially the gain I get from each of the actions and in that round, and I just add them all up because they're all like either 0 or positive numbers. So when I add them all up, it should be some number above 0. But as you approach the Nash equilibrium, and this actually isn't as good of an example. If I do less iterations, you can see it a little bit better. So I'm going to change this variable to 3,000 iterations. Runs quite a bit faster. So this is showing you that the gain as you approach the Nash equilibrium approaches 0 over time. And the more iterations you do, the closer to 0 it gets because it's getting closer and closer to the Nash equilibrium. If you don't understand why that is, go back to Professor Bryce's videos. It's not in the counterfactual regret minimization video that he does, but it is in one of the previous videos in that playlist where he explains why the gain for all of the actions should be exactly 0 at precisely the Nash equilibrium. And as you approach the Nash equilibrium, obviously it would just kind of get smaller and closer to 0 as we're seeing here. So that's what that is, and that's why this number that you're seeing here just kept getting kind of smaller as we went along. And if we do more iterations, you see that it kind of stopped at 0.23, but we can do better than that. We just got to do more iterations and let it go longer. So I'll let it go while I'm kind of describing the code here. Okay, so here I've mentioned in previous sections of this video that I didn't use a tree to traverse it. I'm storing all the info sets in a hash map, and I'm storing them with keys like KPB. KPB would be an example of one of the string keys I use to look up the KPB info set. And I'll look up all the data for that info set that's stored in this info set data object. I also have this sorted info sets. So I sort them by the length of their hash keys. So these first three have hash keys of just one letter. So they're just a length of one. The last ones have a hash key that's got a length 3. They're 3 letters. So they'll all be sorted in that order, where the king and queen and jack will come first, and then these towards the end of the game will come last. And then that way I can kind of iterate through it either from the top of the quote-unquote tree to the bottom, or I can go from the bottom to the top if I just, iterate through this list in reverse order. So that instead of doing a tree traversal, I'm just storing everything in a hash set, and then I've got this sorted list that I can just iterate through whenever I want. And that's, it's not we don't have to worry about the extra memory that it takes to do this or anything, because this is, it's Kuhn poker. It's a tiny game set, so the computer can easily handle this. Okay, so info set data is composed of this stuff, and you can kind of look into this, but basically every info set has a list of has a hash map of actions that it can perform. And so I can do bet or pass for every one of the info sets, and each of those points to an info set action data object, which I'll jump to real quick. So each action has a strategy. So, for this info set, the strategy for the bet action is going to be equal to 0.89. So that's what, this self.strategy value would be for that one. And then it's got a utility value. So that would be this type of thing. So for the bet action, the utility for this info set is 1.17. For this other info set, it's -2, etc. And then there's cumulative gain. I actually don't have the cumulative gain in this table. You can add it if you want to. The place where you would add that would be back in this info set data object. It's right here where I'm printing out the table. Also, I've got this extra code that really isn't necessary if you install tabulate, but this just like prints out the table if you don't want to use tabulate. So you would just if you don't want to, for instance, just install these two packages, you can just comment them out and the code should still work. Yeah, code still works even with them commented out, and it'll print out a decently formatted table, but I prefer to keep those. So anyway, let me finish explaining this. So and each info set has beliefs. So, the beliefs of the info set are here, and that there's, one of them for each of the different possibilities of hole cards for my opponent. So if this were, say, the king info set, then this beliefs hash map would have, so this table just shows whether they have the high card or the lower of the two cards that they could have. Because every time in Kuhn poker, no matter what info set you're talking about, your opponent can always have one of two possible cards, and one of them is going to be higher than the other one. So you can I just labeled this the higher of the two cards and the lower of the two cards. But here, this string is actually like king, queen, jack. So it's going to be like K, Q, J. It's just a little minor point. But basically, this stores these values. So if this were the, say king B info set, then my beliefs would be queen is 2% and the jack is 98%. Okay, so, and then the expected utility, so that's this, but that expected utility is actually a weighted sum of the two utilities individually for the actions, which would be stored here in this info set action data object. Okay, so that's the explanation for kind of how the data is stored in this hash map. So all of this data here is ultimately stored within this info set data object. That's the upshot of all that. And so the key functions, so down here at the bottom, like we're done defining functions, like now here's where I start invoking stuff. So I say initialize the info sets, and this will initialize all of the strategies. If you look at this, it's just taking all of these info set strings that I've hard coded because again the game space is very, very small, and then it initializes the info set data, and in here you can see that it's actually initializing the strategies to be 1/2 essentially 50-50 bet and pass. And if you had more possible actions, and if I had 3 different actions I could do each time, then it'd be 1/3, 1/3, 1/3. That's just how it's going to initialize your strategy to begin with, and then eventually your strategy obviously evolves to more precise numbers. And by the way, this previous one did finish, and you can see that it got much closer to the Nash equilibrium. Never gonna completely hit it, but it's essentially never going to bet when you have a queen. It's always going to pass when you have a queen. Player 1 is going to pass when they are dealt a queen, and that's the Nash equilibrium for Kuhn poker. Okay, so let me go back to down here. So essentially you initialize the info sets once, and then for some number of iterations you're going to do all this stuff, and you're just going to do it over and over and over again. So you're going to update the beliefs, then you're going to update the utilities, and you can see that I'm updating them from the bottom up because I'm iterating in reverse order. So I'll start with King PB and these 3 down here, and I will work my way up the tree, so to speak, to the smaller info sets. And I'll update all the utilities for them, and then I'll update their reach probabilities or likelihoods, and then I calculate the gains for each of the actions, and then I update the strategy using the cumulative gains that I've calculated. You can step into each of those, but essentially you should kind of draw the picture that I gave you in the previous sections of this video for how to think about updating beliefs, how to think about updating utilities. If you just draw that picture and look at this code, you'll be able to figure out what's going on. One kind of confusing thing is, this might be a kind of confusing part because I am switching the pockets here, and you'll just look at the code and you might be confused by that, but essentially that's just because you're switching perspectives from the perspective of player 1 to player 2. You just have to switch these pocket cards. If you think about it for a while, it'll make sense to you, or it won't, but it works. So I wouldn't worry too much about that. And then the likelihoods here, that's again, just refer to the video. Calculating gains and updating strategies, I didn't make a section of the video talking about them because they're super simple, very straightforward. You'll be able to figure those out. So I've covered the potentially confusing parts. I've given you notation for how to kind of write this stuff out and think about it, some specific examples to think about when you're trying to figure out how to update beliefs, update utilities, and calculate the reach probabilities. I've given you the algorithm here that does converge upon a Nash equilibrium. If you are wondering what a Nash equilibrium, if you're wondering what a Nash equilibrium looks like, then just go to Wikipedia, Nash equilibrium, Kuhn poker, something like that. So Kuhn poker, and they tell you what the Nash equilibrium looks like right here. So this is describing in words the the first 3 columns that you see in this table. If you look at the values in the first 3 columns of this table and read through these 2 little paragraphs, they do a really good job of explaining it in words what these numbers are saying. But essentially this is one of the Nash equilibria. Apparently you can pick any number between 0 and 0.33 for betting on your jack. But once you've decided what that number is going to be, all the other numbers follow from that. Okay, so that's all I wanted to explain in this video. Thank you for watching. Good luck.